Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 4.2 on our introduction to logarithmic functions. We should start out by answering the question, what are logarithms? And the short answer is that logarithmic functions are the inverses of the exponential functions that we introduced in section 4.1. So we saw the graphs of exponential functions back in section 4.1. They were either always increasing for exponential growth or always decreasing for exponential decay. But either way, they pass the horizontal line test, which means they are invertible. They're one-to-one. And so they have inverses. Logarithmic functions are those inverses. So now let's take a look at the definition of a logarithm. And it's a little bit weird because logarithmic functions are the only functions that we define in terms of their inverse. And so we say that for b greater than 0 and not equal to 1, which you might remember is the same restrictions we put on bases back in section 4.1 for the exponential functions, then we say that the logarithmic function with base b, written y is equal to log base b of x, and that's how you would read that, log base b of x, where y is equal to log base b of x if and only if b to the yth power is equal to x. So we're taking this logarithmic function and we're defining it in terms of an exponential function. And let's pay attention to what the most important part here is. The logarithm itself is the y value, which is the exponent of this exponential equation over here. In other words, the value of the logarithm is the exponent that would make this equation true. So a good way to read the logarithm by definition is the base b raised to what power would give me x, the thing inside of the logarithm. Right? The base b raised to what power would give you the thing in parentheses. So for example, if we had log base 2 of 8, the way you could read this is the base 2 raised to what power would give you 8? And since 8 is 2 cubed, the answer is 3. So log base 2 of 8 would be equal to 3. This also brings home the fact that logarithmic functions are inverses of exponential functions as well. So consider two functions, the exponential function 2 to the x power, so base 2, and the logarithmic function log base 2. Well, from what we see up here, the exponential base 2 function would take an input of 3 to an output of 8, whereas the logarithmic base 2 function would take an input of 8 back to the input of 3. So it reverse engineers the exponential base 2. This is really the key to this slide. The base raised to what power would give you the thing inside of parentheses. For the first type of problem that we're going to work in this section, we're going to be converting back and forth between exponential equation and logarithmic equation. And the definition of the logarithmic equation that we saw in the previous slide allows us to do that. These two things are equivalent, so you can convert back and forth between the two. So let's discuss how to do that then. The first thing that you'll notice is that the base b is still the base b, no matter which form you're looking at, log base b, exponent base b. So the first thing you'll do is always bring down the base. So log base 3 is going to become exponent base 3. Then what ends up happening is that the other two numbers basically swap across the equal sign, just like the swap and solve method, swapping x and y. So the 4 over here on the right-hand side of the equation moves over to the left and becomes the exponent for the base of 3. and the 81 in parentheses moves across to the other side of the equal sign. And so we get the equivalent exponential equation, 3 to the 4th power is equal to 81. So remember the process. Bring down the base, swap the position of the other two numbers. And it will always work. So now that we've seen an example, try pausing the video here and see if you can convert part B of example 1. And so this one, we've got log base B of Q is equal to T. Less numbers this time around, but the process is still the same. So the base is still the base. We have exponent base T, B, and then the T moves across and becomes the exponent. The Q moves across to the other side. So we get B to the Tth power is equal to Q. Bring down the base, swap the other two numbers across the equal sign. Now let's convert in the other direction, from exponential to logarithmic, and you're going to find that the process works pretty much exactly the same. So once again, the base is still the base, the other two numbers swap. So for part A, we have the exponential equation 2 to the 7th power is equal to 128. So exponential base 2 is going to become log base 2. The 128 on the right is going to move over inside of the logarithm. Logarithms are operators like square roots. They have numbers inside of them. You'll oftentimes see logarithms written without parentheses. So you might see something like log base 2 of 3. If that's the case, it's always just implied that the first number after the logarithm or the first letter is inside. So if you had something like log base 2 of 3 plus x, it would be implied to be log base 2 of 3 plus x. Whereas if you want both things inside of the logarithm, then parentheses becomes mandatory at that point, right? So remember, they're operators. They always have things inside, although sometimes the parentheses are just implied. And so the 128 moves over to the left inside of the logarithm, and the exponent of 7 will move over to the right-hand side. And the equivalent logarithmic equation, log base 2 of 128, would be equal to 7. All right, so now try pausing the video and see if you can convert part B of example 1. All right, so once again, bring down the base. This is an exponent base W, so this is now going to be log base W. The R on the right moves over to the left inside of the logarithm, and the entire exponent of x plus 2 is going to move over to the other side of the equal sign. All right, so even if you have multiple terms, either in the exponent or on the other side, the whole thing will shift across. So if this had been, for example, r minus 3 over on the right, all of that would have gone inside of the logarithm. Now let's take a look at some common abbreviations. Logarithms can have any base as long as it is positive and not equal to 1, but there are some bases that are so common we have shorthand notation for it. The first of these is something called the common logarithm, or common log for short, and this is log base 10. And so if you have a log base 10 of x, we usually just abbreviate that by just leaving off the base. So anytime you ever just see log of something, you're to understand that it is implied to be log base 10. It is the common log. Another very commonly used base comes from the natural base e that we talked about at the end of section 4.1, and this leads to the natural logarithm, or natural log for short. And if you have a log base e of x, this is abbreviated ln of x. And you read this one of two ways, either just ln of x, it's sometimes read, or natural log of x. Either one is okay. Next up, we've got some basic properties of logarithms. And the key to understanding why these are what they are is to remember the way we read the definition. So remember, if you've got log base b of something, the way that you read that is the base b raised to what power would give me the thing in parentheses, which I'm going to write as x for this. So, with that said, taking a look at the first property, if we've got log base b of 1, if you ask yourself, what power would I raise b to get 1? Well, the answer is that no matter what b is, anything raised to the 0th power is equal to 1. And so because the logarithm is the inverse of that, if you plug 1 into any logarithm, you get out 0. Similar reasoning, log base b of b itself, b raised to what power would give you itself? The answer is the first power. Anything raised to the first power would just be the same thing. And then the next two properties together are called the inverse properties of logarithms. And this is because of what we talked about when we covered inverse functions, where if you have a function and its inverse and you compose them, they essentially cancel each other out and just give you x, no matter which direction you compose them in. Well, log base b and exponential base b are inverses of each other. So if we compose them, if we have b to the x inside of a log base b, those will cancel each other out and just give you x. Or if you compose them in the other direction, you take log base b of x and you put it over an exponential base b, that would also just cancel out and give you x. Of these two properties, this one is the most important. This will give us an alternate way of evaluating logarithms than just remembering the definition. That said, if you can remember the definition, that's probably the fastest way to work the problem. But what this inverse property tells us is that if you can write the inside of the logarithm as a power of the base of the logarithm, then those will cancel each other out, and the exponent will be the answer. So let's try it out. Let's evaluate some logarithms using the inverse property. And again, if you can just remember the definition, you can evaluate a lot of these logarithms just by looking at it. But let's start with part A. We're asked to find the value of the logarithmic functions. And we start with log base 2 of 16. So our goal is to write 16 as a power of 2, which we can do. 16 is 2 to the 4th power. And so by the inverse property, log base 2 and exponent base 2 will cancel each other out, and all that we'll be left with is the exponent of 4. So log base 2 of 16 would be equal to 4. Part B is similar. This time we've got log base 1/5 of 1/125th, which would be the same as log base 1/5 of 1/5 cubed, because 5 cubed would be 125. And so log base 1/5, exponent base 1/5 cancel each other out. All we're left with is the exponent of 3. Let's take a look at a few more. For part C, we've got log base 3 of 1. This is actually one of the properties that we looked at on the previous page, but you can still work it with the inverse property as well. Because 1 you can rewrite as 3 to the 0th power, and then log base 3 and exponent base 3 will cancel each other out and just give us 0. For part D, we've got log of 100,000. Again, it's up to you to recognize that because there's no base written here, this is common log, log base 10. And so the goal is to write the inside as a power of 10. Because this is a 1 followed by 5 zeros, 100,000 would be 10 to the 5th power. And so common log, log base 10, and exponent base 10 will cancel each other out. And will just give us the number 5. And then last but not least, we've got natural log of 1 over e cubed. Well, this is not 3, because this is not base e right now. The e being down in the denominator messes things up. So we're going to need to use properties of exponents and rewrite 1 over e cubed as e to the negative 3rd power. Then natural log, which is log base e, and exponent base e will cancel each other out. And we'll just get the exponent of negative 3. So now let's take a look at the graph of a few logarithms. We're going to start by sketching the graph of log base 2 of x so that we can determine its domain, range, behavior, all of that good stuff. Now when we were graphing exponential functions back in section 4.1, those are really straightforward. You just pick a handful of x values around 0. We usually did negative 2, negative 1, 0, 1, and 2. For logarithms, however, picking the x values is the hard part, and the y values will be pretty easy. The trick is to try to pick x values that are powers of the base. That way the logarithm evaluates really nice and easily. So for this one, I want to pick x values that are powers of 2. So let me show you the process. I'm going to pick 2 to the negative 2nd, 2 to the negative 1st, 2 to the 0th, 2 to the 1st, and 2 squared as my x values. Now I want to simplify those to make graphing a little bit easier in a second. 2 to the negative 2nd would be an x of 1 over 4. 2 to the negative 1st would be 1/2. Anything to the 0th is 1. 2 to the 1st and 2 squared. So these are the x values that I want to pick for the graph. The y values, on the other hand, are really easy if you just keep in mind what we were doing here. Because now, if you were to plug these back in, the log base 2 and the exponent base 2 would cancel each other out. So log base 2 of 1/4 would give us negative 2. Then we would have negative 1, 0, 1, and 2. The exponents are our y values. Now, if you were to turn around and graph 2 to the x power now, the exponential base 2, you'll find that you would get the exact same table of values, just flipped. Because log base 2 is the inverse of exponential base 2, all of the ordered pairs flip. But just remember, the x's that you want to plug in are powers of the base. That's how it works out nicely. And so now let's graph this and see what we've got. So our x values go out to 4. And our y values are from negative 2 to positive 2. So at an x of 1/4, a quarter of the way to 1, we're down at negative 2. At an x of 1/2, halfway to 1, we're down at negative 1. We've got 1, 0, 2, 1, 4, 2. And so the graph that we end up getting for this looks a little bit like this. Their growth profile is a little bit like a square root function, but they go down towards negative infinity, right? This graph is going to get closer and closer to the y-axis, the vertical axis, but never quite reach it. Because of that, the y-axis in this case is called a vertical asymptote. We've also got a single x-intercept at an x value of 1 in this case. This shape is called logarithmic growth. And logarithmic growth is truly the inverse of exponential growth. Exponential growth starts off slow and then speeds up as you go. Logarithmic growth starts off fast and slows down as you go, for a shape that looks like this. Let's talk domain and range. So the domain, or the x values from this graph, well, it never quite reaches this x of 0. It just gets infinitely close to it. So the domain is 0 not included with parentheses, but then it does go forever to the right. So the domain is from 0 to infinity. And this is going to be really important once we get to section 4.4. The inside of a logarithm has to be strictly a positive number. Logarithms are not defined for negative values, and logarithms are not even defined for 0. In fact, you could try this out on your calculator. All scientific calculators come programmed with common log and natural log. If you try to do common log of 0 in your calculator, it will give you a domain error. If you try to do natural log of, say, -3 in your calculator, it will give you a domain error. The inside of a logarithm is strictly a positive number. The range, on the other hand, the y values you can get out of this thing, it goes down to -infinity and up to positive infinity. This is always increasing, even if it slows down over time. So the range is from -infinity to positive infinity. Forever down, forever up. And once again, if you go back and look at our graphs of the exponential functions, you'll find that the domain and range flipped, which is what we expect for an inverse function. Let's take a look at one more graph, this one of a logarithm with a base less than 1, to see how it changes things. And so again, the x values that I'm going to pick are powers of the base, so powers of 1/2 in this case. Although because the base is less than 1 this time, I'm going to write it in reverse order and you'll see why. So I'm going to do 1/2 to the -2nd, 1/2 to the -1st, 1/2 to the 0th, to the 1st, and to the 2nd. And so the x values that these correspond to, 1/2 to the 2nd would be 1/4, 1/2 to the 1st would be 1/2, to the 0th would be 1, 1/2 to the -1st would be 2 to the 1st power, and 1/2 to the -2nd would be 2 squared, or 4. So we actually end up with the same x values that we had last time around. This time, however, once we plug these in, because 1/4 is 1/2 squared, that would give us a y value of 2, 1, 0, -1, -2. Again, it's just the exponents for our y values here. And so let's take a look at the shape that we get this time around. So my x values still just go up to 4. My y values this time, -2 to +2. And you'll find that this is flipped from what we had last time. At an x of 1/4, a quarter of the way to 1, we're now up at a y value of 2. At an x of 1/2, we're at a y value of 1, 0, -1, and then at an x value of 4, we're all the way down at -2. And so the shape of the graph that we get this time around looks something like this. This is actually pretty much the same graph we had before, just reflected vertically. Previously we had a graph that looked like this. Now we have one that comes from the top instead of from the bottom. This shape is called logarithmic decay. And it actually has pretty similar features to exponential decay, and that it starts off decaying quickly and then slows down over time. Once again, this time around, the graph has a vertical asymptote. Of the y-axis, and you're going to find that the domain and range are still the same. The domain, the x values, are still from 0 not included to positive infinity, and the range, forever up, forever down, is still negative infinity to positive infinity. So let's recap our graphs from section 4.1 and 4.2. And it's important that you be able to keep these shapes separate because it gets confusing when we cover all these so close to each other. So exponential functions, y is equal to b to the x, are featured as having horizontal asymptotes. They level off to the x-axis, and they have a single y-intercept. You get exponential growth if your base b is greater than 1, and you get exponential decay if your base is less than 1. But because of the restrictions, bases still have to be positive, so between 0 and 1. Now, the inverse of these exponential growth functions flips everything. Instead of leveling off to the x-axis, logarithmic functions level off to the y-axis. Instead of having a horizontal asymptote, they have a vertical asymptote. And furthermore, instead of having a y-intercept, logarithms have an x-intercept. Everything is flipped because they're inverse functions. X and y swap. Logarithmic growth happens when the base of the logarithm is greater than 1. Same for exponential. And logarithmic decay happens when the base of the logarithm is between 0 and 1. Exponential growth and exponential decay are pretty much the same graph, just flipped horizontally, mirrored across the y-axis. Logarithmic growth and logarithmic decay are pretty much the same graph, but this time they are reflected vertically across the x-axis. And so again, it's pretty much just everything backwards compared to the exponential graphs. Just to further illustrate the relationship that we saw when we were talking about inverse functions back in chapter 2, I have graphed two functions here. The one in red is e to the x, the exponential function with the natural base, and the one in blue is the natural log of x, log base e. You might be able to tell that these two graphs are basically reflections or mirror images of each other across the line y is equal to x. The distances are the same, just flipped. And these are reflections across the line y is equal to x because graphs of inverse functions are always reflections across the line y is equal to x. So this is the behavior we would expect to see. Right? E to the x has a y-intercept at 0, 1. Natural log of x has an x-intercept at 1, 0. Any ordered pair on e to the x would just be flipped to land on natural log of x. So we've already mentioned several times in this section that logarithmic functions and exponential functions are inverses of each other. If all you have is just a single exponential function, b to the x, or a single logarithmic function, log base b to the x, then all you have to do is change it to the other type to find the inverse. Sometimes it gets more complicated than that, however. Well, fortunately, we can still find the inverse functions using the swap and solve method that we first covered back in section 2. Swap x and y, solve for y. Now, in particular, the solve portion of this is going to require a trick. And what we're going to need to do is end up using the conversion process that we first looked at back in example 1. All right, so if you're trying to find the inverse of a logarithmic function, in order to solve for y, you're going to need to convert it to an exponential function, and vice versa. If you have an exponential function and you're trying to find the inverse, you're going to have to convert it into a logarithmic function. Let's take a look at an example. In part A, we've got f of x is equal to log base x plus 2. And remember that because there's no parentheses here, there are implied parentheses around just the first thing after the logarithm, x. And so this would be the function y is equal to log of x plus 2. All right, so now I'm going to swap. Y becomes x, x becomes y. So now our goal is to solve for y. And ultimately, we're going to need to convert this thing, but before we do, before you convert, you always want to isolate either the logarithm or the exponential function. So I need this logarithm on the side by itself. So I'm going to subtract the 2 across to the other side. And so we get x minus 2 is equal to log y. Now I can convert. So I'm going to swap this equation to read in the opposite order, just to make the conversion easier to see. This is entirely optional. You could convert it when it's on the other side. But just like before, I'm going to bring down the base, which is implied to be 10 in this case, because it's a common log. Everything on the other side of the equal sign comes over and becomes the exponent. And the stuff inside of the logarithm, which is just y this time around, moves over to the other side of the equation. And now y is actually already solved. We're good to go. So f inverse of x would be 10 raised to the x minus 2 power. Again, it's just the swap and solve method, but for the solve part, you need to convert. So let's take a look at one more. This time we've got f of x is equal to log base 3 of x plus 4. And this time the plus 4 is inside of the logarithm because it's inside parentheses. And so let's take a look at what the inverse would be. So this would be y is equal to log base 3 of x plus 4. The swap part of the swap and solve. Y becomes x, x becomes y. Now I need to swap. Now I need to convert. And this time, I'm not going to rearrange it. You can if you want to. I'm going to leave it on the right-hand side just to show the way that it looks. So once again, I'm going to bring down the base. Log base 3 becomes exponent base 3. The x comes across to the right-hand side of the equal sign and becomes the exponent. And everything inside of the logarithm, y plus 4, moves over to the left-hand side of the equation. So the arrows don't look as nice when you don't rearrange it like this, but the idea is still the same. The base just turns to the other kind of base, and the other two expressions move across the equal sign to the other side. We're not quite done. We do need to finish solving for y, which is really easy at this point because we just subtract 4 from both sides. And so we get y is equal to 3 to the x minus 4. So f inverse of x is 3 to the x power minus 4. All right. For part A, we started with a number outside of the logarithm. That number happened to end up inside the exponent. For part B, we started with a number inside of the logarithm. That happened to end up outside of the exponent. That will always happen, but you don't have to memorize it because, again, it's just part of the swap and solve method. Now let's go in the opposite direction. And the idea is going to be the same. You're going to swap, and then in order to solve, you're going to convert this time from an exponential to a logarithmic equation. So starting with part C, we've got the function g of x is equal to e to the x plus 1. All right, so in order to do the swap and solve, I'm going to swap it out as y equal to e to the x plus 1, just a notation thing. Swap, y becomes x becomes y. Now I need to solve. Just like before, I need to get the exponential on the side by itself before I convert. So I'm going to subtract the 1 across to the other side. And this time I will rearrange the equation again. Just swap the order. Now I convert. So exponent base e will become log base e, which we abbreviate as ln for natural log. The entire expression x minus 1 to the right of the equal sign moves over to the inside of the logarithm, and the exponent of y moves across to the other side of the equal sign by itself. This one's already solved for y, so this is the inverse. G inverse of x would be the natural log of x minus 1. So try pausing the video here and see if you can find the inverse to the h of x in part D. All right, so once again, I'm going to start off by writing y is equal to 6 to the x minus 2. Y becomes x becomes y. And this time, the exponential function is already on the side by itself. We just got a base 6 raised to a power. The power is just a little bit more complicated this time. So I'm ready to convert. Exponent base 6 is going to become log base 6. And then everything else jumps across the equal sign. So the x on the left moves across and goes inside of the logarithm. And the entire exponent y minus 2 moves over to the left. In order to solve for y now, we just add the 2 across to the other side. And so we get y is equal to log base 6 of x plus 2, or h inverse of x is equal to log base 6 of x plus 2. And I can leave off the parentheses because it's just the x inside of the logarithm. Or you can leave the parentheses. Both are fine. Before we wrap up the section a little bit, let's ground these idea of logarithms in reality. So logarithms are extremely common in mathematics, in physics, in engineering. They show up in tons of applications, but we even see evidence of logarithms in the real world, even though we might not always recognize that that's the case. And these often show up in the form of what are called logarithmic scales. Because what logarithms are good at are taking a phenomenon that could take on a wide range of values, just drastically different numbers, and then kind of pulling that down into a smaller range of numbers that are easier to comprehend. One example of a logarithmic scale is called the Richter scale for rating the intensity of an earthquake. And the Richter scale's definition is the log, common log, base 10, of I, which is the intensity of the earthquake that you're measuring, divided by I0, which is a small benchmark or standard for kind of the base power of an earthquake. And so I0 is just a fixed number. I think it was originally defined as the smallest earthquake that would show up on the Richter scale, although that said, our instruments have gotten a lot more advanced since the scale was first created, so that might not no longer be the case. That said, I0 is a constant, a very small benchmark earthquake. And so let's answer a couple of questions then to understand how this logarithmic scale would work. For part A, we're asked what would be the Richter scale rating of I0 itself. So the earthquake that you're measuring is what goes in the numerator. And so if we're trying to measure I0 itself, this becomes log of I0 over I0. The denominator is always the same, which since these are the same, this would just reduce to 1. And so this is log of 1. 10 raised to what power would give you 1? The answer is 0. And so that makes I0, this small benchmark earthquake, the start of the Richter scale, starting at 0. Although again, because our instruments are more advanced, you can actually have earthquakes that people can't feel, which would have a negative Richter scale value. For part B, we're asked, what is the Richter scale rating of an earthquake 100 times as intense as I0? In other words, the intensity of the earthquake we're measuring is 100 times the intensity of I0. Well, let's plug that into the formula and see what we get. So this would be log of the I that we're measuring is 100 times as strong as I0 divided by I0. So those reduce away, and this is just log of 100, which would be 10 squared. And so log base 10 of 10 squared by the inverse property would just be 2. So an earthquake that is 100 times stronger than our benchmark would be a 2 on the Richter scale. For part C, we're asked what would be the Richter scale rating of an earthquake 1 million times as intense as I0. Because again, the earthquake intensity can vary wildly. You could have a rumble so small, only someone directly at the epicenter could feel it, or you could have an earthquake so large that it could topple buildings. The difference in magnitude there is massive. Well, let's see. What would the rating be for an earthquake 1 million times as intense as I0? Similar process to what we did in B. So the intensity we're measuring would be 1 million times larger than I0. So we plug that in for our intensity we're measuring. Once again, the I0s will cancel. So this is just common log of a million, which is 10 to the 6th power. So log base 10 of 10 to the 6th would be a 6 on the Richter scale. And so what we're doing is we're creating a range of values that can vary by tens of millions, and we're breaking it down into a number that essentially falls between 0 and 10. In fact, I think the largest earthquake ever registered was somewhere in the 8s on the Richter scale. And the idea of a log base 10 scale like this is that every time the earthquakes get 10 times as intense, the number goes up by 1. So a Richter scale of 0 is our baseline. A Richter scale of 1 would be 10 times more powerful than a 0. An earthquake of magnitude 2 would be 10 times more powerful than a magnitude 1. A magnitude 3, 10 times more powerful than a magnitude 2. Now the Richter scale is only one example of logarithmic scales that we see in everyday life. Another one, probably that people run into more commonly, is the pH scale for measuring the acidity of a solution That's actually a log base 10 scale as well. And even the way we measure the intensity of sound, decibels, is also a log base 10 scale. So these are things that we run into from time to time. And that is it for our introduction to logarithms here in section 4.2. As far as the types of problems go from this section, the first type of problem, and this is going to be important moving forward, is converting back and forth between exponential equations and the equivalent logarithmic equation, and vice versa. So going in either direction. We got a taste of why that was important with the fourth type of problem in this section, finding the inverse of a function as part of the solve for the swap and solve, but it will also be very important in section 4.4 for just solving equations in general. So that will come back. The second type of problem in this section was evaluating logarithmic functions, either by the definition or through the inverse properties that we talked about, writing the inside of the logarithm as a power of the base. You should be able to graph basic logarithmic equations. Transformations also work on both the exponential equations and the logarithmic functions we're looking at, but you're not going to see anything like that here in Math 101, just basic logarithmic equations. Make sure you can handle that. And then last but not least, of course, finding the inverse functions, which, as we talked about, are important. It's important to remember that you need to convert as part of that process. All right, as always, if you guys have any questions, please make sure you let me know, and I will see you in the next video.